I'm Andrei, Johan's colleague from Intel Espoo, Open Source Technology Center of Intel. And I wanted to give you a lightweight overview of what Zephyr can do in networking. About 2.5 years ago, we started Zephyr as an operating system and as a project, open source project. And since the very beginning, we started it with the IoT in mind. So it was meant to be kind of powering IoT. These days, Zephyr finds a lot of more users elsewhere as well, but IoT was always a primary reason for us to exist. We started with borrowing an TCP stack or IP stack from Contiki. It's a micro IP stack, and lived with this for about half a year or a year. And after that, we realized that we're actually not fitting the size. There were several fundamental problems with the Contiki operating system micro IP stack. It was actually meant for a very low resource devices, even lower than we were ever targeting, like some kilobytes or like 5 kilobytes, 10 kilobytes, 16 kilobytes. We were looking at a slightly higher resource usage. Then it was full of everything was global. There was a single buffer. You were unable to have multiple interfaces, multiple applications using the IP stack. And what was also important is that it was not integrated to our configuration system. So we were unable, it was very hard to modify. So we, of course, hacked together something that worked, but it also departed us so far from where Contiki was, then it didn't make any practical sense to live with it. So we took a hard decision and replaced the stack. And we actually looked outside for the good candidates and haven't found any. For the one fundamental reason for that is that the IP stack essentially is the glorified buffer processing. So, it's all built around how do you work with buffers. And the way buffers are managed is very central to an individual to the operating systems. So we decided to write our own stack. And it took us about a year and a half, like in an hour time. So we had a team of 3-4 people writing the stack. And it has seen a daylight first in the Zephyr 1.6 almost a year ago. And since then, it started to get a good popularity, a good traction in the community. We have actually, we're very happy to see external contributions. In fact, the Contiki guys, we are still working with them. And they actually just recently gave us LWM2M that I'll be mentioning a little bit later. Now, so the year after we published the stack, we have a fairly decent configuration for the class of the smart IoT nodes type of device. We're fitting in the space under 200K of RAM and under 200K of ROM type of devices. We have a dual mode IPv4, IPv6. That's TCP and UDP. We actually do IP forwarding. I'll mention it a little bit later in the following slides. Now, for IoT, so we had to support a number of the radios that are IoT specific. And one of them is a 15.4, which is also based for the Z-Wave. Another one, Bluetooth. I want to mention that our team, or the set of softwares that we do, is probably some of the most advanced in the open source community in sending IP over Bluetooth. We actually do have probably the most sophisticated implementation of IPSP protocol. So it's not broadly used, unfortunately, out there, but you could send over Bluetooth LE, you could send IPv6 using 6LoWPAN. Important addition to our stack was that we have a model where we could use the high-level chip together with the chip running Zephyr and mimic the high-level interface of that chip, for example, a full Mac stack, to pretend to be the Zephyr IP stack. That allows us to use things like HTTP server, for example, running on the Zephyr while actual IP stack runs on the other chip. So that's called IP offload. So we have a fairly decent set of technologies, including 6LoWPAN implementation for both Bluetooth Low Energy and 15.4. We have a Ripple, which is a way to manage the routing information in the mesh type of the IP network. We have a security in place, both for TCP and UDP, so TLS and DTLS. We have HTTP client and server, co-op, MQTT, MDNS responder, and LWM2M, which was contributed by Contiki guys. And you could get a lot more at the networking documentation, and we have everything's public that we do. Now, I think nothing speaks better for what we can do than actually samples that we have. I don't want to get into the diagrams and the design graphs. But so one of the pinnacle of all technologies that we have, except for Bluetooth for now, is the border router for the IP-based network. So we have an application that allows Zephyr to be the central device for the 15.4 mesh network, route the IP data in and out, act as the root of the graph of the ripple. So it's the root of the mesh network. So that's RPL, DODAC root. We do have HTTP server running on Zephyr. That server supports WebSocket. Using the same WebSocket, we are actually able to forward the entire shell, not even the console, but the shell, so bidirectional shell, into the browser. So you can actually have your browser on your PC and Zephyr over the network, say Ethernet. And we do have, with the co-op, we can control the nodes connected to the border router in the 15.4 network. We run that stuff on the NXP Freedom board with the 2520 wired to that. That's a 15.4 transceiver by Texas Instruments. If I'll have enough time, I'll try to show the video how the thing looks in dynamic. It's quite curious. Beyond this, in samples of Zephyr that you can get from GitHub, we do have, for example, a telnet implemented for Zephyr. So it allows you to access the Zephyr shell over IP. We do have IRC board. We do have a BSD socket implementation. I want to have a disclaimer here that the BSD sockets are not native to Zephyr. So you could use that if you have your software that you want to port on the sockets, but please be aware that that would cost you memory, extra copies. Otherwise, we are fairly optimized, and we have a very minimal amount of data copying in the Zephyr. The couple of latter examples get us closer to like this conference topics, if you will. So Zephyr can be used, and I believe that this is one of the most interesting uses for this audience, as a communication enabler for Linux. Now, Zephyr supports USB. We do have a couple of modes here. One, the WPAN serial allows Zephyr to export whatever data it receives on the 15.4 radio over USB directly to Linux, so that the data can be consumed by some user-land application. To give an example, one of these applications is the Contiki-based border router called Sparrow. So it actually built as a user-land binary for Linux, and it consumes the serial radio, and then through the TAP interface, it gets into the Linux networking. The second one is the USB driver that allows Zephyr to be used as a 15.4 device for 82.15.4 subsystem of Linux kernel. The kernel driver for the latter one is due to be out this year, so we are working to make it out. So plans. At the moment, we're working to finalize the high-level chip support for the Wi-Fi networks. It kind of departs us a little bit from IoT, but there are many people who are asking for this. The same way we want to implement some 4G LTE modem. There are a few modules that we could hook to Zephyr. We are working to have the thread protocol supported. So Thread Alliance is the way, it's one of these standards that meant to rule the IoT. So it's a mesh. It's a standard for IP networks for the IoT sensors. One thing which, unfortunately, I probably won't have much time to describe is the support for emulation. Now, we are partnering with a small Polish company called Antmicro that who has the emulator called Emulate. So that's their site, emulate.org. Now, that allows you to run the native binary images built, say, for some x86 embedded, or for STMicro, or a number of others, into your Linux distribution. It's actually a fairly resource-consuming thing because it's written using Mono, but nevertheless, it's super cool. And why it's super cool is that you can run multiple copies of this on your PC, and you could they also provide a network media emulation. So actually, the devices could speed out the Mach frames of a 15.4 into this commonly controlled network media emulation, so that you can actually run the mesh simulations. And in fact, actually, we have done one using some 5-6 emulated nodes. And what was it? Yeah, and then there was an emulated 35, whatever. Anyway, so another Texas chip that consumes these frames for the Linux. And we had a border router running in Linux. So essentially, all what I showed you previously in the network border router, but running on a single PC. So, which is real cool. So, I mean, it's all public. This is important thing is that these things exist. They cost hundreds of thousands or millions, and that is free. That one is free. That's why we were very interested. Now, the next thing that we are planning to do is to have support for Open Connectivity Alliance API set. So that's another cure for the world's problems. Intel is very active in this. This is, again, an API that meant to unite all the IoT in the world. And Samsung, by the way, supports it as well, and there are a lot of Samsung products currently that's supporting this API. Another thing that we're working on is the sophisticated test automation for the stack. Unfortunately, there's very little out there, unlike Bluetooth, by the way, available for free or for a reasonable cost to test the IP stack. There's very little. We've really done a lot of the homework to search. So, but we found a very good standard and a set of tools that allows us to create and use already created test suites for the communication protocols, including IPv6, including CoAP, including MQTT and stuff like that. That's called TTCN3. This is a standard, actually. So the tool that we are planning to use is Eclipse Titan project. Ericsson was backing it a lot. Last but not least, the technology that we want to support is 802.11e if there's enough drive. That's 802.11e is a more advanced version of, sorry, 802.15.4, what I'm saying. 802.15.4e is a more advanced version of 802.15 that supports the time-slotted network hopping and a number of other advanced things that makes it a little bit more reliable. There's a lot of work. So far, we haven't seen a lot of drive for it. So if there will be a lot of requested, we will consider supporting it. So that's about what I wanted to say. So if you have any questions, please go ahead and ask them. In the meantime, maybe Johan can help me dragging the video while we're showing it.
Okay.
Hi, thank you for the talk. Could you please elaborate on TLS about memory requirements, computing requirements, typical performance?
For TLS?
For TLS, yeah.
Well, I don't have them from the top of my head, frankly. Well, the entire this border router that you see now is playing good. So is actually altogether is 166K of RAM and 200K of ROM. Now, performance-wise, cannot tell you. We do have actually tools supported. We have an iPerf ported for Zephyr, and this is you see how the nodes are actually joining the Ripple network here. So this it's a real time. Every little circle here is the board with the 15.4 power supply.
Okay, thank you. The next question. Okay.
My question is TCP/IP stack on Zephyr, was it written from scratch, or did you use some other IP stacks which is open source, like LVIP or some any other stack?
Thank you. Good question. We considered that. Well, actually, for many stacks, our APIs, our licenses are incompatible, so we couldn't just grab things, right? And lightweight IP, for example, has a totally different model of the buffer management. We consider that a little bit, but no, we wrote it from scratch in the end, yeah.
And what is the license of Zephyr?
It's Apache,
It's
Apache
Apache,
2.
right.
Yes, it's a permissive license that you could show things that you want and hide things that you don't want to be shown.
Yeah. Did you measure some performance for IP stack, or it's not target for Zephyr? So
It's very hard to compare, right? So you need to really have the same hardware. So we did measurements, of course, and it showed us some numbers, but it's very hard to say, you know, whether it's fast or slow, because, you know, we didn't port other stuff.
Agree. Thank you.
Okay, one more.
Thanks for presentation. I want to ask about emulation. You say in Planish what you have plans to add emulation for this operation system. Did I understand correctly what we can emulate? We can run these binaries for this also on Linux, and we can emulate communication between different binaries, like we can emulate full mesh network on Linux on one PC.
Correct. Moreover, we talking to, you know, it's like a small community of the RTOSs that actually work with this stuff, like Contiki, like there's a FreeRTOS there. We actually been debating with the guys that we wanted to have a virtual interoperability verification available. I'll try to, if I have time, I'll try to organize that at our side. So what all you need to do is essentially is a powerful server that has that stuff running, so you can have your device binaries built for supported architectures and the peripherals, so Emulate needs to support this thing. And you can upload them to that computer and run one of these copies as a node in the mesh network, see if it interoperates. You see? So yes, that's an exceptionally powerful thing. It's a kind of rocket science, frankly, but it's, if made right, this is real cool.
Yeah, thanks.
Okay, next question. Probably one from me. You mentioned a number of times offloading, and especially offloading for IP. What functionality offloaded to other chips or in these kind of devices?
To give you an example, if you take one of the popular chips that people use with Arduino, so that's I think it's called AT-Wi-Fi, their popular name. The chip inside is a Atmel, it's a Wing 1500 chip. So it interface to the applications look like the following. So you have a binary that is built for a platform that exposes a very high level interfaces. So as an associate with the network, send the data, like resolve the name and stuff like that, right? So on top of that, we are putting a very thin layer of the Zephyr offload API implementation, so that, for example, HTTP server could send the data using, in the end, the functions from that binary that actually go to the chip. So that's a level of offload, yes.
Okay, thank you. Well, I see. One more question.
I have one more question about community of the Zephyr. How big is open source community, and who does Zephyr now, and what companies are involved, and
well, we had a whole slide set about this yesterday. But so of the big players, so the corporate companies that are there, it's Intel, it's NXP, it's Linaro that pulls actually. So that's ARM open source, right? The Nordic, right? So what else? What did that? Synopsys, of course. Yeah, so the smaller ones like Runtime.io, Oticon, there are more companies actually considering joining, I know. So there's a company-wide. So a lot of people contribute from those companies. Now, many people contribute actually from their Gmail accounts, so you don't know whether they are private individuals or they work for the companies. We have seen the mailing list is very active. It is, I mean, you know, for like 3 weeks, it's like 5,000 messages. So that's a good, healthy amount of discussion there. So yeah, it grows. Please don't forget that the embedded world is not something that people quite often, you know, publicly talk about, right? So that's why the Zephyr is in a way a disruption there.
Okay, thank you. And what is the exact type of the license for Zephyr?
It's Apache 2.
Apache 2.
Apache 2
and
license.
no any commercial license, just Apache 2.
That's just Apache 2, no strings attached.
Plain and no. Okay, thank you.
Yeah.
Okay, if we don't have any more questions, you can think about which one is the best and use the stickers. So probably postpone this until the next presentation about Bluetooth stack.
I mean, perhaps we could have a voting like at the end of the
yeah.
block. Yeah. So,
Okay.
But thank you very much, everyone, for the very good questions. Hopefully it was interesting for you. So thank you.
Yeah, absolutely. Thank you.